Hello again. Let's keep going. Roots of polynomials. All right. The next tool in our toolbox for finding roots of polynomials is something called Descartes' rule of signs. So what has to be true is this has to be written in standard form. Remember, the powers have to just be decreasing. So first you put your highest power, then your next one, and so forth. Okay, the way this is stated in words is a bit convoluted. Once we work through it a couple of times, it will make more sense. The quantity of positive real zeros is either equal to the number of changes in the sign of the coefficients, or it's off by a multiple of 2. The number of negative real zeros is the same thing, but instead of working with f of x, work with f of minus x. Honestly, stating it is confusing. Working through a few examples will make it clear. Okay. So here is a polynomial. Let's use Descartes' rule of signs. So question 1, is it in standard form? Yes. It's already written with the higher power 6, then the fourth power, then the second, then the first, then the constant term. If it's in a weird jumbled up order, the first thing you have to do is change it to standard order. Next, count sign changes. And when I say sign changes, I mean of the coefficients. So this is a positive coefficient, then a negative one, then a positive one, then a positive one, then a negative one. How many times did it change? It changed once, twice, no change, 3 changes. So there were 3 changes in sign. So how many real roots? How many positive real roots? It could be 3 because of that 3, but I can also be off by 2. The good news is I can be off by having fewer. So instead of 3, I maybe have 1. Suppose, for the sake of argument, there were 7 sign changes. Then the quantity of positive real roots could be 7, or 5, or 3, or 1. If the number of changes in sign was 4, the number of positive real roots could be 4, or 2, or 0. Okay, 0 is a perfectly acceptable quantity, but negative numbers don't make any sense because we are counting something. Okay, so this function might have 3 positive real roots, might have only 1. Then you can do this again for f of negative x. So what we're going to do is we're going to compute f of negative x is 2 negative x to the 6th minus 3 negative x to the 4th plus negative x squared plus 5 times negative x minus 2. The good news is, what's negative x to an even power? It's just x to that power. So this is just going to be 2x to the 6th minus 3x to the 4th plus x squared. Even powers don't care about plugging in a negative x. But this term right here changes. Instead of the original being plus 5x, now it's minus 5x minus 2. Okay, so I'm going to clear everything off in order to keep discussing this. So in summary so far, our number of positive roots was either 3 or 1. We then computed f of minus x, and we got 2x to the 6th minus 3x to the 4th plus x squared minus 5x minus 2. And honestly, all I'm really doing is I am not changing the sign of the coefficient for even powers, but I am changing it for the odd powers. And now we do the same argument. How many sign changes? This is plus to minus to plus to minus to minus. So there was 1, 2, 3. 3 sign changes. So now, how many negative real roots could it have? Either 3 or 1. So how many positive roots? Either 3 or 1. How many negative roots? Either 3 or 1. Could it have 3 of both? Yes, it's a degree 6 polynomial, so it has at most 6 roots. Maybe it has 3 positive and 3 negative roots. What it can't have is something like 4 positive and 2 negative roots. Okay. So the way this could be very handy to us is suppose I find a positive root, and then I find a second positive root. It can't just have two positive roots. It either has 3 or 1. So if I manually find 2 positive roots, there must be a third one to find. Similarly for negative. Also, suppose this had suppose it was degree 7, and you go through the same work and you find the number of positive roots is 5 or 3 or 1. And you find that the number of negative roots is 4 or 2 or 0. It can't possibly have 5 positive and 4 negative because it's only degree 7, so it has at most 7 total. So if you found 5 positive roots, you would know that it doesn't have 4 negative roots, and that would help simplify your search later. So I can combine this with some earlier stuff and use some logic and simplify stuff down a bit. So we found, using Descartes' rule of signs, the number of positive roots is either 3 or 1, and the number of negative roots is also either 3 or 1. And that's just exactly what the book just did. I just thought I'd do it writing out by hand. And so here they're just stating what we just said. It either has 3 positive x-intercepts or 1 positive x-intercept. It also has 3 negative x-intercepts or 1 negative x-intercept. Notice in Descartes' rule of signs, the end result is here's how many positive roots it maybe has. What it absolutely did not do was tell us what those roots are. It didn't tell us how to find them. Okay. Now the rational roots theorem is something that gives us some candidates. Now, it only applies if I have a polynomial where every coefficient is an integer, aka a whole number. Could be positive or negative, but I don't have like fractions or weird numbers as coefficients. Okay. If a fraction is a rational root, then the numerator must be a factor of the constant term. The denominator must be a factor of the leading coefficient. If every coefficient is an integer and a fraction is a root, the numerator must be a factor of the constant term, and the denominator must be a factor of the leading coefficient. Notice this says nothing about roots that are not fractions. It just says if there is a fractional root, then it has to look like a certain thing. If a root isn't a fraction, oh well, this doesn't say anything. So let's apply this theorem to the following polynomial. First thing first, are all the coefficients integers? Yes. If not, the rational roots theorem just isn't going to help. If all the coefficients are fractions, you can do some tricks, but sometimes you just are out of luck. But all the coefficients are integers, so we're fine. So then what you say is if p over q is going to be a root, then p is a factor of the constant term. What's the constant term? 4. And q is a factor of the leading coefficient, 2. So what you need to do for the second step is list factors of the constant term over factors of the leading coefficient, including pluses and minuses. So it's plus or minus. What are the factors of 4? Either 4 or 2 or 1. What are the factors of 2? Either 2 or 1. And the way I tend to like to do this is I take the smallest denominator possible and then list out all the possible numerators, and then I look up to the next possible denominator. So if I make my denominator 1, I could have plus or minus 4 over 1, plus or minus 2 over 1, plus or minus 1 over 1. If I made my denominator 2, I could have plus or minus 4 over 2, plus or minus 2 over 2, or plus or minus 1 over 2. Now there's some duplicates in here. 2 over 2 is the same thing as 1 over 1, so ignore it. 4 over 2 is the same thing as 2 over 1, so that didn't give us anything new. So ultimately, the potential rational zeros are plus or minus 4 over 1, plus or minus 2 over 1, plus or minus 1 over 1, and plus or minus 1 over 2. So how many numbers is that? It's 8. Okay, it looks like it's 4, but remember it's a plus or minus. There's 8 numbers in that list. What degree is this polynomial? 5. So can all 8 of those numbers actually be roots? No. In general, this is going to give you way more candidates than could possibly be roots. It does not say they are all roots. It just says if a root is a rational number, in other words, one integer over another, then it has to be in this list. It doesn't even tell you that the roots of the polynomial have to be in this list. It just tells you any fractions that are roots have to be in this list. Okay, so I'll clear off my pen marks. The book is surely about to say exactly the same thing. Yep, factors of 4 over factors of 2. Formal possible ratios, there they are. And there they are, plus or minus 1, 2, and 4, but also plus or minus a half. Okay. If there is a rational 0, it's in this list of possibilities. Okay, how about the same thing? But now we actually want to find the zeros. So now what we have to do is we have to combine all of the previous things. So first of all, our first most basic observation, it's a degree 3. So it has at most 3 real roots. What are they? I don't know yet. Let's use Descartes' rule of signs. So, as written, is it in standard form? Yes. So now I count sign changes. The coefficients go positive, positive, negative, negative. There is 1 sign change, positive to negative. So there is 1 positive root. That's actually really nice. There is guaranteed to be a positive root. All right. Let's compute f of minus x. And remember, the odd powers change and the even powers don't. So this becomes negative 3x cubed plus 4x squared plus 5x minus 2. How many sign changes? There are 2. So there are 2 or 0 negative roots. Okay. So I'm going to clear this out to save some space, and then we're going to move on to the rational roots theorem. So what we found so far, and I'll put it up here, the number of positive roots has to be exactly 1. The number of negative roots is either 2 or 0. Okay, now let's apply the rational root theorem. If there are any rational roots, well, do I have integer coefficients? Yes. So if it has rational roots, they have to be of the form plus or minus factors of the constant term, that's 2, over factors of the leading coefficient, that's 3. The factors of 2 are 1 and 2. The factors of 3 are 1 and 3. So overall, I can have plus or minus 2, plus or minus 1, plus or minus 2/3, and plus or minus 1/3. That's a lot of things to check. It's 8 things to check. But 8 things to check is a lot better than I have absolutely no idea where to begin looking. Also, some of these are easier to check than others. So let's make a list. It could be 2 or negative 2, 1 or negative 1, 2/3, negative 2/3, 1/3, negative 1/3. And let's just start computing them. And if you don't have any other reason to start somewhere else, start with the easy one. What's f of 1? F of 1 is 0. Hey, just by plugging it in. If I just plug in f of 1, I get 3 plus 4 minus 5 minus 2. That's 0. So 1 is a root. Now, how many positive roots did this function have? By Descartes' rule of signs, it had exactly 1. We found it. That means all the other positive numbers cannot possibly be roots. I don't have to check them. It only had 1 positive root, and I found it. Hooray for me. All right, what about negative roots? Well, let's try them. What's f of minus 1? Again, I may as well start with the easy one. F of minus 1 is negative 3 plus 4, so that's a 1, plus 5 minus 2, not 0. I wasn't computing exactly what it is, but it's not 0. So negative 1 is not a root. What about f of minus 2? Okay, Well, now I actually have to write it out, so let's try it. F of minus 2 is 3 times negative 8 plus 4 times 4 minus 5 times negative 2 minus 2. This is negative 24 plus 16 plus minus 2, which is 0. Yay! So negative 2 is a root, which means how many negative roots does it have? It does not have 0 of them. It must have 2. Also, it's a degree 3 polynomial, which means it has at most 3 roots. So as soon as I have already found one positive root, and now I know I'm looking for 2 negative roots, that's going to be all of them. Okay. So we found 2 roots, 1 and minus 2. So let's see where that gets us. What we could do, by the way, is we could just manually compute what are f of minus 2 and f of negative 2/3, sorry, and f of negative 1/3. So if we were to do that, let's see. F of negative 2/3 is going to be, I'm trying to fit it on this slide, which is going to make it a little crowded, I'm sorry. I'm just putting it up here. So f of negative 2/3 is going to be, come on, stupid thing, 3 times negative 8 over 27 plus 4 times 4 over 9 minus 5 times negative 2/3 minus 2. This is negative 8/9 plus 16/9. Negative 8 plus 16 is 8, so this ends up being just 8/9. Then I have to add 10/3, and then I have to subtract 2. That's not going to be 0. The quantity of ninths just doesn't work out, so this isn't 0. So that's not a root. Now, I can't immediately conclude that negative 1/3 must be a root. I know there's a second negative root. I just don't know that it's a rational number. I don't know that it's a fraction. But let's go ahead and check it. Okay, I'll try to put it here in this box. Okay, I'm really just trying to find all the roots before clearing out all the work. So if I compute f of 1/3, we end up with 3 times 1/27 plus 4 times 1/9 minus 5 times 1/3 plus 2. So 3 times 1/27 is 1/9 plus 4/9 is going to be 5/9. Then I need to subtract 5/3, and then I need to add 2. Again, my quantity of ninths just isn't working out, so I don't think negative 1/3. Oh, I computed 1/3 instead of minus 1/3, so this would be a minus 1/27, and this would have been a plus 5/3. So now I have negative 1/9 plus 4/9, that's positive 3/9, that's a third, plus 5/3 plus 2, no, it's just too big. There's too much stuff. Oh, but this is a minus 2. I don't know why I'm writing all my numbers wrong. I'm sorry, this is actually 0. So negative 1/3 is a 0. So now we know that the roots are 1, negative 2, and negative 1/3. Okay, now I'll clear all this off. So we found some roots of 1, negative 2, and negative 1/3, which means I can find factors of x minus 1, x plus 2, x plus 1/3. However, that's not this function. The reason is, if you multiplied all of this out, you'd get an x cubed and then a bunch of stuff, but I don't want x cubed, I want 3x cubed, which means f of x can be factored, but I need to put an extra 3 out in front of that whole thing. And some of you might now say, well, let's take that 3 and multiply it in here, because then I don't have any ugly fractions to look at, and that's how most people would do it. And there's the factored form of f. Okay, so I just wanted to do that all out by hand, but here's just the typed up version. Yes, the maximum number of zeros is 3. Descartes' rule of signs tells me there is one positive real 0. Also 2 or no negative real zeros. If there are rational zeros, they have to be in this list. Is exactly what we found. Let's just test them, and yeah, test 1 first if you can, because it's usually the easiest. Hey, it's a root, therefore x minus 1 is a factor. Now the book's technique is going to differ slightly from mine. So at this point, we have confirmed x minus 1 is a factor. So what they do is they actually factor it out. Do the long division. Do x minus 1 out of 3x cubed plus 4x squared minus 5x minus 2. A lot of people ask, can we do synthetic division? Yes. I generally do long division all the time because synthetic division only works when you're dividing by x minus a number. If you're trying to divide by 3x minus 1, synthetic division doesn't work. If you're trying to divide by x squared minus 1, synthetic division doesn't work. So I usually just do long division because it'll always work. If you like synthetic division and you can do it correctly, by all means, go ahead. So if we do this long division out, this, we need a 3x squared. That gives me my 3x cubed. Then I minus this. I subtract that. I have 7x squared, so now I need a 7x. Gives me a 7x squared minus 7x. When I subtract that, I get 2x minus 2. So I'm going to have a plus 2, 2x minus 2, no remainder. And that's exactly what they got right here. Okay, and like a lot of people are like, oh my God, why do you do it so fast? Because I've practiced. I'm not some sort of weird god at this. I've just done it a bunch. And honestly, if you guys want to be able to do it that fast, practice. How many times do you have to do a polynomial long division to get it to be about that fast? I don't know, a couple hundred of them. Which sounds like a lot, but really isn't. If you just churn them out, you'll get this good. It's not because I'm good. I have just done it a bunch. Anyway, there's the factored form. And now all we have to do is factor this. Okay? But this is a quadratic equation. You can factor it by I if you happen to be really good at it. Also, because it's a quadratic, you can use the quadratic formula. So we want to solve where is 3x squared plus 7x plus 2 equal to 0. That would be x is negative 7 plus or minus the square root of 49 minus 4 times 6 all over 6. Negative 7 plus or minus the square root. 49 minus 24 is 25. The square root of 25 is 5, so this is either negative 1/3 or negative 2. And there are your two roots, negative 2 and negative 1/3. So as soon as you find a single root, you can factor it out and be left with a simpler polynomial that you can then maybe just try to work with directly. And as soon as you have a degree 2 polynomial, the quadratic formula ends the problem for you. Oops, clear that. And there we have it. Okay, so we're going to end this video here. Practice some of these things. There are a whole lot of sample problems that say, here's a polynomial. Why don't you factor it? Why don't you find the roots and factor it? Practice, 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 practice. Do the odd ones. The answers are in the back. Check your answers. Come to office hours. Ask questions. Can you factor a polynomial by combining things like Descartes' rule of signs and the rational roots theorem and doing polynomial long division? Is like a really foundational skill in this course. It's something that we can give you a problem and pretty quickly weed out who's been paying attention and who hasn't.